So I don't know what these people are doing, why they find this so intriguing on vacation, but for some reason, as you'll see, they're standing at the end of the runway to do fence surfing, I guess, ultimately, holding onto the top bar of the fence and sort of horizontal. I guess this is a take on the United San Francisco truck behind the plane idea, relevant in some way to what we're talking about. Just enjoy yourself, relax.
Au ciel d'été, on chante des blancs moutons. Avec les ondes des pures, la mer, bergère d'azur infinie. Voyez, près des étangs,
Would you like to be doing that?
ces grands roseaux mouillés. Voyez, ces oiseaux blancs.
All right, that's enough of that.
Et ces...
What else is running? So this is a lead-in, I guess, to what we'll talk about today. We've got some time to go. But a lot of the things we've been doing have been for very, very simple geometries. Bernoulli has been for a stream tube. We've done slightly more complicated things with Reynolds transport theorem, looking at conservation of mass and also conservation of momentum. And so that really, Reynolds transport theorem is for conservation of those two quantities are the two behaviors that are needed to do real-world simulations of real-world problems. And so these are just some quite complicated simulations that use those principles in a model to be able to do things that you would see actually these days in movies. And so special effects, when you see curtains blowing in the breeze and it's done by animation, then there has to be some fluid mechanics principles to give it the right feel for what you see being an interpretation of reality, because we judge things based on our own knowledge of processes. So the water sloshing around in this from this hose as it goes in is being represented, actually I didn't bring it today, but the same idea as individual balls of water. If you can imagine those all being injected out of this nozzle, then if you can track them using Newton's second law, F equals ma, and their collisions are taken care of in terms of conservation of mass, then you can write some equations that allow you to be able to do this. And so you see the kind of rendered simulation on the top, and on the bottom you see this evolving grid that the water flows through. So it's a bit of an oversimplification to say that you're thinking of these as lots of particles of balls that are reacting to gravity, and due to the accelerations in being ejected into this system, it's actually a little different from that. And the idea is that this stuff on the bottom left is a grid with these little boxes allowing for fluid to flow into them and fluid to flowing out of them. You have to have fluid flowing out to allow fluid flowing in. And so you can enforce the laws of Newton's second law, basically, conservation of momentum, in three directions, and conservation of volume, which is just really or mass, which is a scalar. And with those four equations, you can solve for the unknowns in the system. And the unknowns would be velocities in three directions and fluid pressures. So you need four equations to do that. And so what we'll talk about today is at least the first step in doing that. So if to solve these very complicated problems we need both conservation of mass and conservation of momentum, typically they're not written in the format of Reynolds transport theorem. They're written in a differential format as a partial differential equation. And so today we'll end up talking about the first one of these, which is conservation of mass written as a differential equation. And the relevance of that is that these free surface what are called Navier-Stokes flows, after two scientists who talked about fluid flows, Navier and Stokes, solve for momentum in the system. Some flow systems are much, much simpler than that. And this looping behavior, perhaps some of the things that, if you're a petroleum engineer or if you're an environmental system engineer, for instance, then you're dealing with fluid flow in porous media. And so the previous simulations we looked at solved for momentum, conservation of momentum. So throw a ball at a wall, hits the wall, bounces back. You're conserving momentum in that case. It's this v squared over 2g term that's in Bernoulli. In some flows, for instance in porous media flows, the velocity is so small that compared to the other terms, the pressure head and the elevation head, it's trivial. And so you can throw it away. And so you can make calculations in porous media flows by flowing away this momentum term, which means that the momentum equations that you would have to solve and honor, you can throw away as well, and you just have to solve conservation of mass. But if you solve conservation of mass, you also have to be able to account for the fact that it's a viscous flow and you're losing energy. You have to apply, I think the color scheme in this is that red is for a higher pressure, blue is for a lower pressure on the other face. And so you're using pressure up to push this thing across the cube where these are the individual sand particles, and it's going through the pore spaces only as this multi-phase flow of oil within the system. And so if you throw away the momentum equations, then what you have to do is be able to incorporate these frictional losses within the system, which are what this term that we've called H sub L, or losses, in our class last time. And so we'll end up by putting together the equations that allow us to be able to solve these equations, which certainly, if you're, as I say, you'll see in the rest of your career here, because it's basically the essence of reservoir engineering is being able to solve for problems like this. How much fluid do you get through the system if you try sucking it out? Basically the question. And so that's where we'll ultimately go today. I don't want this, I'm going to close it just because I don't want to overplaying what we'll talk about. So that's kind of where we're going today. So I guess that's where we are. I thought it would be worthwhile just revisiting the things we talked about last time, as we always do, to recapitulate. And if you remember, what we said was that we can solve these systems as one-dimensional systems along stream 2 using Bernoulli's equation. And we can write Bernoulli's equation that has these either energy inputs or energy outputs, as in a turbine or a pump, and also fluid losses within them. And we can write it in one of two ways. We can write it in one that represents kind of physical behavior, when we're solving physical problems, and one in which we write it in terms of a chemical approach, where we want to look at, say, chemical transformations, burning hydrocarbons in a jet engine as an enthalpy increase in a system that pushes a plane into the air. And so the Bernoulli one is pretty straightforward. It's everything we've seen before. We've written it as we had it before: pressure head, elevation head, and velocity head. It happens to have this little extra term on here, but we're not going to worry too much about this. This is related to whether the flow is homogeneous and uniformly at the same velocity, or whether it has some change in velocity as it goes across the end of the stream tube. And two other terms which are important. The first being a pump head, again being a length, because the other terms are lengths, and a head loss. We said that the pump head is always positive if it's a pump, and negative if it's a turbine. We always have to write it from upstream to downstream. We could imagine putting this pump head in here, and typically the head losses are thought of, they're basically frictional losses due to flowing within here, which is the head loss that occurs along the length of it. And we drew this little diagram last time to be able to add each of these terms together at the upstream portion to represent the individual heads plus the um, pump head at the upstream location, and then stack them all up on the right-hand side plus the head losses at the downstream location. We know that these units have to be units of head, and so sometimes we can write this in terms of a term. This is called the Darcy-Weisbach equation. Not important that you remember that. But it talks about how much the head loss occurs as a function of a loss coefficient and v squared over 2g, the velocity head. And so we know from this that since v squared over 2g has the units of length, then this has to have no dimensions. Typically, and we'll talk about it in pipe flows, that this number typically is of the order of 0 to 1, but can also be larger than that. Likewise, the pump head that we have to put into the system, we can define in terms of power. This is in watts. Uppercase W dot is watts, as we've used uniformly before. And again, to make this a head, these are the units. This is a mass flow rate. Mass flow rate is always positive, as we said before, not depending on in or out, but always positive. And gravitational acceleration. And again, the units of this should work out to the right magnitude. We can look at it as a power per unit mass flow rate, I guess this would be. Can be a loss or an input into the system, but this is really what you want. This is when you say a pump has 20 kilowatts or 50 horsepower, then W dot is what we're talking about. Uppercase W dot is the power. So those are the units for and the behavior for the physical exposition of this equation. The chemical exposition are again the same. It has the elevation head, velocity head. The magnitude of pressure head is included in the enthalpy. So H is equal to internal energy per unit mass plus, I think, pressure over density. This goes in here, so it's included in here. This H, by the way, came up in a conversation after last time, is not this H. Not the same units, not a head, but the units of enthalpy have to be, in this case, they're units which are equal to energy per unit volume. So the units of enthalpy are equal to energy per unit mass. Did I say volume? And so if you look at the units of this, then the units of this would be what? This is a Newton meter. And I'm running out of space, but if I would go over here to keep it going, a Newton meter is a 1 kilogram meter per second squared, right, this term here. And then meters and kilograms from the remainder. And so this is equal to units of meters squared, second squared. A strange number, but of course it's the same as velocity squared. Velocity is meters per second, velocity squared is meters squared, second squared. And so clearly these have to be the same units to be able to match up. And again, it's important in writing this equation that this is a mass flow rate which is a scalar value and always positive, kilograms per seconds, and that this is between the upstream and the downstream. Only works if that's the case. The heat energy that's put into the system is positive if you're putting energy into the system, burning something as in a jet engine, and it's positive if you're putting work into the system, as in pumping something. And so those are the sign conventions that we have to deal with. But I think hopefully you can see the parallels between these two. They're really the same equation. All they are is written differently to include enthalpy in this particular case, to include the internal energy that you might want to put into the system. Okay? All right. So the things I wanted to do today with that, any questions I guess we should ask? So the things we want to do today is go over some examples, which we'll spend most of the time, and also talk about differential analysis. These have all been derived from Reynolds transport theorem. We didn't really do the derivation, but that's where they come from. Most of the modeling that's done, the examples we looked at earlier today, and you'll look at on the video for Friday, are for flow in porous media or flows. They require that we use not an integral statement of what's going on, which is what Reynolds transport theorem is, but a differential equation, d2p dx squared, etc. And so we'll get to talk about that, but we'll spend most of the time talking about examples. Okay. All right. So those are the two expressions that we would want to use. And so let's talk about how we might use them. So here's an example that has two tanks, which are connected by a pump, which is putting some pump energy into the system. It's flowing between a lower tank, which is being pumped up to a higher region. We know the elevation difference between them is 100 feet in this particular case. We know that there's a frictional head loss along this pipe, and we can think of that as, it's not really an arrow, but it's, well, I guess probably just write it as a head loss, which is equal to KL divided by, multiplied by V squared over 2G. The velocity that we're talking about is always the velocity in the pipe. It's usually prescribed. So this is an average velocity in the pipe, as opposed to the velocities in the tank, which probably don't matter if we write Bernoulli, because if we use the large tank assumption, then the velocity at 1 is going to be equal to 0, and the velocity at 2 would also be equal to 0, right? If we're smart. So there's a drag in the pipe, which is this. This is the average velocity in the pipe. This loss coefficient can change with velocity, but in this case it's constant. And it's 20 in this particular case. And there's a certain amount of pump head put into the system. And the question is, what is the equilibrium flow rate that this gets if this pump head is defined in terms of the head as a function of flow rate. So this is the pump characteristics, if you like. This vertical axis on the right hand side is the pump head, the energy, the power that's put into the pump in some respects, as a function of flow rate. At very low flow rates, the pump with its given power can raise water a high distance, 200 feet. If you want to pump it at 2 cubic feet a second, it can barely move water a foot, which is this magnitude here. And so this is the characteristic curve of a pump. A pump can pump very high differences in elevation at very slow rates, or very small differences at very high rates. Makes sense, right, in terms of the power of the pump. We can write Bernoulli for the system in which we deal with it here. I guess usually you should realize that this equation here that we're going to use, a modification of this, is just, can be written, can be kept in this case in terms of lengths. So what do we know? If we write a streamline that goes through here, from upstream to downstream, then the pressure here is atmospheric. The pressure at the downstream location is atmospheric. Big tank assumption, velocities are 0. Elevation between point 1, which can be 0, and then this is 100 feet. Then this is 0. Well, keep Z1 minus Z2. We know the difference between them is going to be 100 feet. British units in this case. The head loss we know is going to be this friction loss, V squared over 2G. And the pump head that we know, if we write an equation for this line, it's this equation. And you can substitute this in. So when the flow rate is 0, then the pump head is equal to 2 minus 0 times 100, which is 200 feet of water. When the flow rate is equal to 2, then this term here is equal to 0, and the pump head is equal to 0. And so this is just the equation of the pump head, which can go into here. And so now we have an equation where the only terms are, we have a length, we have a pump head, and we have a head loss. And each of these two other terms, this is absolutely defined. HP is written in terms of a flow rate, so this is written in terms of Q. But also this loss term is written in terms of Q as well, right? Because we know that from continuity that the velocity is equal to Q over cross-sectional area within the pipe, whatever that cross-sectional area is. And so if we know what that cross-sectional area is, we can write this as, this gives us velocity squared is equal to Q squared over A squared. So in other words, we have a velocity squared term which lives in here. So this whole term here is written in terms of Q. This term here is also written in terms of Q. And we know the length of 100. And so we only have one equation. We have one unknown value of Q, and that's how it turns out. It's done slightly differently in here, but we could work through it. So this is the equation that we're working with. We happen to know that this is equal to 100 feet. We know that the pump head here is given by this term here. We know that the head loss here is given by this term here. And we can convert this Q squared into what we've done. So this, V squared is just equal to Q squared over A squared. And so if you make those substitutions into this equation 1, then we end up with an equation to solve. And if we solve it, it ends up not to be very easy because it's a quadratic, but we can get it nonetheless. And it comes out to be a value of flow rate. So you can solve it in one step, or you can solve first for HL, but regardless you get a result for flow rate out of the system. So I think the easiest way to think about it is that you have one equation, you have two unknowns, one of which is Q and one of which is the velocity. You can make that velocity into a flow rate, Q, and therefore you only have one unknown. Okay? Yes? Units of Q are always volume per unit time, meters cubed per second. K has to be unitless because this is a unit. This is a unit of length. V squared over 2g is a unit of length if you do the calculations, and so the multiplier has to be 0 units. Right? For the same rationale as this here. So this is a unit of length, so this is meters, and so this term here is also meters, and so meters to meters has to be no dimensions. Okay. All right. All right. So that's one. So we'll go through a few today. Same ideas. We'll always use the same equation. If we So this is an example looking at gasoline being pumped to an upper level through a pipe system. So it's gasoline, so it has a density which is less than water. It goes through a pump at a flow rate of 0.12 meters cubed per second, that's Q. The head loss between the sections is equal to this term 0.3 V squared over 2. I think it should be G in the way that we looked at it before. You could think about adding a G to this. What will be the difference in pressure between sections 1 and 2 if we have this amount of power in the system? So this power is what we've called uppercase W dot. And so if we look at that, then we know that, for instance, this term here is going to be what we'll use. So the pump head is going to be equal to W dot over mass flow rate times G. So I might write that down. So HP is equal to the power in the pump divided by the mass flow rate times G, which is equal to the small w just divided by G, I think, just for reference. Positive if in, negative if a turbine. And so we use the same equation again, slightly differently. So if we multiply this whole equation through by, I guess, rho G, then P over rho G just becomes P, etc. So that's all that's being done here. And if we multiply this by rho G, then we also turn this term into this lowercase net shaft in. So that's where this terms come from. What do we know? So here we have a cross-section. Here we have a cross-section and a flow rate. And so we know that V2 is equal to the flow rate divided by the cross-sectional area of flow. From continuity, we know that V2A2 is equal to V1A1. And so if we rearrange that for this, then we get that V1 is equal to V2 times the ratio of the cross-sectional areas. So if we know what this is, then we know what V2 is. If we know what V2 is, we automatically know what V1 is as well because we know each of these areas. So we have a velocity V1 that we know. We have a velocity V2 that we know. Yeah, okay. And are they both, yeah, they're both probably, oh no, they're different diameters. So they're two different velocities. And so if we look at what we know in the system, we don't know what the pressures are here. We don't know what pressure 1 is. And we don't know what pressure 2 is. And from one equation, we're not going to be able to get two variables, but we can get the difference between them. And so if it's 10 kilopascals difference, it doesn't matter whether it starts off at a very high pressure at the lower one. It'll just be 10 pascals different at the other one. We just know the differential. So we want to be able to figure out P1 minus P2, so we can rearrange the equation in terms of that. So this equation 1 is just Bernoulli, written in terms of the pressure head, the velocity head, the elevation head, the work into the system, and the losses in the system. And we have to figure out what we know. We've said we know what the velocities are at points 1 and 2 because we know the flow rate and we know cross-sectional area, so we know each of the velocities. We know the difference between the elevation Z1 and Z2. Remember again, flow rate is from upstream to downstream. So the flow rate is through 2 as the downstream location. So we have to write the equation in terms of upstream as 1, downstream as 2. So Z1 will be 0, Z2 will be equal to 3. And we know what the losses are because we've been given the losses in terms of this term here, 0.3 v squared over 2. And we know what the net shaft work in because we've been told that it's 20 kilowatts, except 20 kilowatts is uppercase W, not lowercase w. And so that's something we have to account for. And so the rest of you can see the calculations here. If we know the flow rate, we can calculate what V2 is. If we know V2, we can calculate what V1 is. And we have numbers for each of these. We know the elevation difference. If we know that these are equivalent to each other, we can rearrange this equation as equal to lowercase w is equal to G times uppercase W over mass flow rate and G. Which is exactly what you have written down here. I'll make it smaller rather than do that. So lowercase w is equal to power divided by mass flow rate. Mass flow rate is just equal to the volumetric flow rate, meters cubed per second, multiplied by density, which is kilograms per meter cubed. So this is kilograms meter cubed. So kilograms per second. And so we end up with a value for this, which is, so this is 220 kilowatts. This is 20 kilowatts. Newton meters per second, so joules per second. And the rest is just the flow rates that we have in the system. And so we have this, so that's this term here. And we have the loss within the system given as this velocity, which in this particular case is written in terms of V1. Okay, I guess that's the other important thing that's given in the question. This, because there's two pipe diameters, the coefficient that defines loss in the system has to be defined relative to one of the pipe sections. There are two velocities. There's a velocity 1 here, there's a velocity 2 here. Which one do you use? And so that's what this 1 here that's added here says, use the velocity that's in pipe 1, which is why in this last expression here for the loss, this has been the velocity that's used in pipe 1. So this is this 15.28, which is this 15.28, which is this. And so now, without getting in the nitty-gritties of all these things, we've got the velocities in the two pipes. We've got the elevation difference, 3 meters. We've got the power converted to this lowercase w through this expression here. And we have the loss defined in terms of the velocity in pipe 1. The only thing we don't know is what we solve for, and that's the pressure difference between the upstream, the downstream and the upstream. And so in this case, it comes out to be minus 197 kilopascals. So in other words, it's saying that the upstream, so this negative 197 means that the pressure here could be 0, and the pressure up here would be plus 197. Was it kPa? Which means that you're pumping uphill. So you're starting off with a tank that could be open to atmospheric. By applying a pump and pushing it uphill, you're providing the impetus to put energy into the system to move it up to this higher pressure state where it goes downstream. Usually when things flow downstream, it goes from high pressure to low. In this particular case, because you're putting energy in at this point here, which is this pump head, is the pressure that's downstream is increased because you're physically putting energy into the system. Okay, so it just becomes an issue of being able to do plug and chug. I think this is the last one. Maybe we'll do. Whoops, didn't mean to do that. Well, so the final one is looking at an example that is just actually related to what we talked about. Yeah, go ahead.
Why didn't you multiply it by density times gravity?
Because you can use it in any way. We could have you could have written this equation and solved it as in units of length. We just have had to convert it so that this is, just because we wanted pressures. So you could either calculate, P1 minus P2 over unit weight, and you could solve this equation for that, and then multiply this by the unit weight of water, and you get the same result. So.
And then you get like a given fact that the W shaft N equals the big W over down there.
Yeah, it's, here you mean?
Yeah, to the left of that, yes.
You are given this. What was the question? Are you given this?
Now, is that like a given fact that relationship always works between the W shaft?
Oh yeah, it's this standard equation that we have here. So it's a good one to remember. It's just this relationship. It's just two ways of writing it. This is power, mass flow rate, and gravity. So this would be power per mass flow rate. So lowercase w shaft in equals power per mass flow rate. And W dot equals power, equals joules per second, equals watts. So yeah, so these two equations, which are Bernoulli written with energy losses in them, from a kind of chemical standpoint with enthalpy and a physical standpoint, can be applied universally. This, of course, here is exactly the same quantity as power. So this is power as well. So this is rate of thermal energy in, which is power. Energy divided by time. Rate of energy in is thermal power. This is mechanical power, if you like. And again, remember the conventions. Positive if in, and negative if out. So in other words, if you're burning something in it, that's positive thermal energy into the system. And if you're putting power into it in a pump, so positive is a pump, and negative is a turbine. And so you remember when we did this example, the 20 kilowatts was a positive quantity that went into that expression. So this was plus 20 kilowatts because it's a positive magnitude. Right? Okay, final one, just very quickly. So pump storage, we talked about pump storage, but also part of pump storage is running the flow through a dam in the first place. What's the maximum power you can get out of a turbine if you have a flow through it from an upper reservoir that has some potential energy? So water sitting here has some potential energy. So again, we can do the streamline between an upper point, location 1, and a lower point, 2. We can write Bernoulli as we had before. If it's on the surface here, 0 pressure. If it's on the outlet here, 0 pressure. If we know the elevation difference between these, which are Z2 minus Z1, we know those. Big tank assumption, big reservoir assumption, throw this away. If we have losses going through this pipe, then we'd have some loss in the system, but it's asking us what's the maximum possible power. So in that case, it's only maximum if there are no losses in the pipe. So let's assume that this is equal to 0. That's what is done in this case. So there's no frictional losses in the tube that brings the water to the turbine. And so the question is, what is the value for this if we know what the downstream velocity is? The easier way to do this problem is that ultimately this flows into a big tank as well. And so you could do this at point 2, where this velocity would be equal to 0. And so this term would drop out. But in this case, we're not given that luxury because we have a velocity here. And so we have to use that. And so it becomes just a matter of, so we have a velocity, 6 meters per second, that is coming through here. So we know this. So the only thing we don't know, I think, is HP. And so we can calculate HP just by solving. I mean, I would do this as this. HP is going to be equal to Z2 minus Z1 plus V2 squared over 2G. And we also know that this HP is equal to, we wrote it before, right? Power divided by mass flow rate divided by G. This is our standard relationship, this term here. So we know that z2 minus z1 is 50 meters. We know that v squared is equal to 6 meters a second squared. And so we know everything here. We know gravity. We know, do we know mass flow rate? No. Do we have a mass flow rate? How do we get mass? Oh yeah, we do have a diameter. Oh yeah, we have a diameter. So we have Q is equal to velocity times area, and area is equal to pi d squared upon 4. And we know that velocity is equal to 6 meters a second. So we have a mass flow rate, because mass flow rate is equal to, doesn't want to write, it's thinking. Mass flow rate is equal to volumetric flow rate times density, which is equal to Q rho. And so we know Q, we know density of water, we have M. And the only parameter we don't have coming out of this is uppercase W dot. Mass flow rate we know, gravity we know, everything on the right hand side. This is 6 meters a second. And if we do the calculations where we assume that there's no losses in the system, this term is 0. You can scroll down and the power you get out of the system is 2.23 megawatts. It doesn't matter what the power is, but you can calculate it. Okay? So just like Bernoulli, you have to make sure you only have one unknown in your equation. And if you have two unknowns, you possibly have to use continuity. Mass flow rate upstream, mass flow rate downstream have to be equivalent, so it allows you to constrain, get one of the terms out if you have two values of velocities. All right? How are we doing for time? That was the last example I was going to do. So just to reiterate, these are fundamental questions, fundamental equations. We won't ask you ever to derive these expressions from Reynolds transport theorem. We won't use it with Reynolds transport theorem, but these equations come from Reynolds transport theorem applied for conservation of energy within the system. Along a streamline between an upstream location and a downstream location, constrained between a pipe, or if you like, a stream tube or a streamline, and the parameters are velocity, streamline velocities, V1 and V2, elevations, positive upwards, Z is positive upwards, pressure is positive for a pump, negative for a turbine, always positive. Mass flow rates, always positive. Doesn't matter whether it's going in or out, it's a scalar value of mass flow rates. Okay? And so if you know these equations and you know these conversions, it's all scribbled over now, but this conversion here is a key conversion. I guess the other one is the conversion to torque. So what is it? Shaft work is equal to torque times angular velocity, angular rotational velocity. I think that's power, right? Power is equal to torque times velocity. Yes, that is right. It's power, right? So torque is a force times a lever arm, so Newton meters, and this is a rate, so Newton meters per second, which are joules per second, which are watts. Okay, so those are the three relationships that you need here. Okay. Well, all right. So we'll see. Right. So that's the first part. Yeah, go ahead.
Yeah, so for question 517, the mass flow rate sign was changed.
Which one was this? Okay.
Yeah, we used the W shaft out.
Oh yeah. Okay. So this sign convention. Yeah. All it is it notes that if you're putting energy into the system, then this value should be positive. And so, I don't think you need to do this. I think you need to do the calculation and to figure out what this magnitude is. If it comes out as being positive, then it means you're putting energy into the system as a pump. If it comes out that this is negative, then it means that you're getting energy out of a turbine. Okay, yeah, good question. And that's really all they've done here. They've just made this transformation to do that. But I think it's easier not to think about that. All right, what else will we do? Well, why don't we do something else? I'm just going to do this. So let's make the point that so what we were going to do before was talk about differential analysis. Or differential analysis. And so we've used Reynolds transport theorem. And so we've derived all of our energy equations using this. This is what's given us those two Bernoulli-like equations that are on that previous sheet. For chemical behavior and kind of physical behavior. And in most kinds of analyses we'd like to do, all the kinds of things you'll do in petroleum engineering, you'll solve differential equations to solve for fluid flow in porous media. And along the lines of this little example we showed at the beginning of class. And so what we could do is we could take Reynolds transport theorem, RTT, and try writing it for a cube that happens to be this little differential cube that we've always talked about. We've talked about this sign convention, or coordinate convention, where we have this right-hand rule. This right-hand rule, right? And those are distances in the x direction, y direction, and z is positively upwards. And we could look at conservation of mass. And you'll recall that our conservation of mass equation looks something like density times rate of change of volume plus volume times rate of change of volume times rate of change of density plus sum of the mass flow rates equals 0. So this is week 6 stuff. So we could imagine that we have some stuff flowing within this system, and it goes in with some velocity in the x direction, and it comes out with some velocity in the x direction plus a change in velocity in the x direction. And these individual lengths that we have here would be a small length in the x direction, a small length in the y direction, and a small length in the z direction. We know that the area of this upstream face in this convention is going to be dy times dz. And so what we could do is we could try writing this conservation of mass term instead of for an arbitrary control volume, which is what we've done, we could write it for this differential cube. And so let's take the first term, which is sum of the mass flow rates. So we'll take this one first, which is going to be equal to what? This is the sum. A mass flow rate is a velocity times a density times an area. And so if we write it for this particular cube, then if we follow our sign convention, we have a density, we have an area, which is dz times dy. And in terms of the velocities, we have a velocity going in, and so our convention for this is that it's negative Vx, right? It's going, the normal to the boundary is outwards, the flow is against that normal, and so by convention flow in is negative, which is this. And we have a velocity coming out of here. And this would be equal to, this is outwards, so it's plus velocity in the x direction plus whatever the change is in that velocity. And we're going to use this little transformation that we did before, and we're going to multiply it by 1. And 1 is dx over dx. And so if you look at this, then these two terms cancel because they're negative of each other. And we're left with density dz dy dx from here, and multiplied by the rate of change of velocity in the x direction with dx. So this is the sum of the mass flow rates, but of course it's only the sum of the mass flow rates in the x direction. So what we want to do for conservation of mass is we know that we have to sum all of the 3 directions. And so if we do that same manipulation for the other directions, so for y and z, so in other words, in the y direction we'd have vy coming in, etc. So in other words, the sum of mass conservation for all directions is just going to be density. What's this term here? This is just the volume of our cube. And so this is rho v, and it's equal to rate of change of velocity in the x direction with x, plus rate of change of velocity in the y direction with y, plus rate of change of velocity in the z direction relative to z. Should be a partial, I guess, rather than the full differential, but you get the idea. And so this would be Vz upwards here. So that's our differential form of mass balance when there's no changes in the system. If we look at the right-hand side of this, we could look at 2 cases. So if we look at the accumulation term, so this is the rate at which fluid accumulates within the control volume. This is the rate at which it goes across the boundaries, in or out. And they have to balance. If we look at these 2 accumulation terms, the volume multiplied by the rate of change of density, or the density compared to the rate of change of volume, they actually represent 2 different systems. So you could think of this as a gas reservoir, where you have a compressible gas which changes density as you change its fluid pressure. Or you could think of this as a liquid reservoir where the density really doesn't change as a function of pressure, but as you compress the reservoir and the reservoir squeezes down as you change the pressure, then the volume of the control volume changes. And so we could look at either one of those cases. We'll look at maybe this one only. And what do we want to do with that? So we can write this term as a volume times a change in density. So a change in density is d rho with respect to time, right? The over dot means d rho dt. So this is a bit of a squirrely one, but nonetheless. And we can again multiply this by 1. Let's choose the one that we write it by being a change in pressure divided by a change in pressure. So this is pressure, this is density. And so the reason for writing this is that now this is written in terms of how pressure changes with time. And so what we could do is if we equate this, so we have now this term here, which is this, and we have this term here, which is this, then we can just add them to each other. So this is a plus sign on an angle. So in other words, V rho dot plus m dot equals 0 allows us to write this as volume, change in density with pressure, change in pressure with time is equal to density, volume, and I won't write all the terms in the brackets, but d velocity x dx plus the others. And I will divide both sides through by density, and I will multiply both sides through by volume, and I will note that this term here, by definition, 1 over rho change in density with pressure is equal to compressibility, which we defined in our second class. And so this expression is written as compressibility, change in pressure with time is equal to change in velocity in the x direction with x plus change in velocity in the y direction with y plus change in velocity in the z direction with z. And the reason for writing this in terms of pressure is that if we have a way of taking this conservation equation, which doesn't include anything about losses, and write something like Darcy's law, which we don't have time to really explain, which links a flow velocity with a permeability, a viscosity, and a change in pressure, and a negative sign. And if we substitute this in here for this velocity, then we end up with an equation which looks like this. I know we're kind of going over, but let's just finish this off. This is pressure with time, and this is and other terms. This is pressure, d2p So the good news is I'll never ask you to reproduce this. But the big picture of this is that what we've used is we've used conservation of mass only to be able to write a continuity equation. And so this continuity equation is this, that says the rate of accumulation of fluids is equal to the rate at which it crosses the boundaries for conservation of mass. And so that's exactly the same as what we've done in terms of conservation of mass in terms of Reynolds transport theorem, but it's written as a differential equation. What we'd like to do is write it only in terms of pressures, and the way we do that is we use Darcy's law, which accounts for an upstream pressure going to a lower downstream pressure, expending pressure as it goes downstream, which means it's got frictional losses within it. And that frictional loss is what gives this flow equation through permeability and the viscosity of the fluid, the loss within a system. We're not solving for momentum, but intrinsically we've allowed for energy losses within the system that allow us to be able to explain exactly what's going on. And so this is exactly what we've talked about in terms of, for those of you who came in a little late, or maybe we started early, was that if we look at this behavior here, then this is exactly what's going on in this particular system. So this is this looping system, upstream pressure red, downstream pressure blue lower, and that's what's driving flow across the system. Viscous friction along the walls of these pores is what's included in Darcy's law to give us this resistance and flow loss, and that's what represented in the system.